Okay, let me ask you something. You've got a hard drive sitting in your computer, maybe a terabyte, maybe 4 terabytes if you splurged. And you think, all right, that's a lot of information. That's a lot of bits. Movies, photographs, documents, the entirety of your digital life packed into a little metal box that fits in your hand. That feels like a lot. Now look at the room around you. There's light bouncing everywhere. Off the walls, off your hands, off the screen. Just light. Electromagnetic radiation flying around at 300 million meters per second, going everywhere, doing everything. You barely even think about it. It's just light. Here's what I want to tell you today. That light, that thing you're barely thinking about, carries more information than your hard drive. Not just a little more. Not twice as much. We're talking about a difference so vast that comparing your hard drive to a beam of light is like comparing a drop of water to the Pacific Ocean. And if you'll give me a little time, I'm going to explain exactly why that's true and why the implications of that fact go all the way down to the deepest foundations of physics. Because this isn't just about storage capacity. This is about what information actually is at a fundamental level. This is about entropy and thermodynamics and quantum mechanics and ultimately the holographic principle, which is something I spent a good chunk of my career thinking about. So let's start at the beginning. What is information? Most people, when they think about information, they think about meaning. A message, words on a page. But that's not what a physicist means when she says information. When we say information, we mean something very specific and very precise. We mean entropy. We mean the number of distinct microscopic configurations a system can be in. And we learned how to count that from a man named Claude Shannon who, back in 1948, worked out the mathematics of it with such precision that we've been using his framework ever since. Shannon's idea was essentially this. The amount of information in a system is proportional to the number of yes/no questions you'd have to ask to fully describe it. Each yes/no question is 1 bit. If you have a coin, heads or tails, that's 1 bit. If you have 2 coins, you need 2 bits. If you have a hard drive with 1 trillion bits, you need to ask 1 trillion yes/no questions to fully specify its state. Now, a hard drive works by aligning tiny magnetic regions. Each region is either pointing up or pointing down. That's your bit, 1 or 0. A 1 terabyte drive has roughly 8 trillion of those little magnetic regions, each one storing a yes or no. That is genuinely impressive engineering. The people who figured out how to make that work deserve enormous credit. But here's the thing. Every one of those bits is stored in a physical chunk of material that takes up space, that has mass, that needs to sit on a shelf. The density of information storage is fundamentally limited by how small you can make each physical element. And at some point, you run up against atoms. You can't subdivide matter forever. But light? Light is different. Light operates under an entirely different set of rules. Let me tell you about photons. A photon is a quantum of light, a little packet of electromagnetic energy. And a photon can carry information in multiple ways simultaneously. It has a frequency, what you perceive as color. It has a polarization, the orientation of the oscillation of the electric field as it travels through space. It can be in a superposition of different states, which is a quantum mechanical thing that I'll get to in a moment. And crucially, when you're talking about information capacity, it's not just single photons that matter. It's the collective electromagnetic field with all its modes, all its frequencies, all its configurations. Here's an analogy. Imagine a string. You can pluck it, and it vibrates at its fundamental frequency. But you can also have overtones, vibrations at twice the frequency, 3 times the frequency, and so on. A real string vibrating in a complex way is a superposition of all those modes at once. An electromagnetic field in a region of space is like that. But instead of one string, you have an infinite number of modes, all of them potentially carrying information, all of them potentially in any number of quantum states. Now, I want to tell you something that took me a long time to really internalize, and I've been a physicist for a very long time. The amount of information that can be carried by light, by electromagnetic radiation, scales with something you would not naively guess. Jacob Bekenstein was a physicist, a brilliant one, who, back in the early 1970s, was thinking about black holes. And he worked out something that seemed at first like it was just about black holes, but turned out to be about everything. He found that the maximum amount of information you can store in any region of space is not proportional to the volume of that region. It's proportional to the surface area. Let that sink in for a moment, because it's strange. If I give you a box, you'd think the amount of stuff you can put in the box, and therefore the amount of information needed to describe that stuff, should scale with how big the box is on the inside, with the volume. That's your intuition. That's a completely reasonable intuition. But Bekenstein showed, using thermodynamics and the properties of black holes, that the real limit is set by the area of the boundary of the box, not its volume. This became known as the Bekenstein bound. And what it tells you is that the universe is, in some deep sense, less voluminous than it looks. Information doesn't fill three-dimensional space the way you'd think. It's encoded on surfaces. It's encoded on boundaries. It's encoded on, if you want to use a word that might sound familiar, holograms. Now, why am I telling you this in a video about light? Because here's the connection. Light, electromagnetic radiation, is precisely the kind of thing that can encode information at the surface of a region, not in the volume. Light travels along light sheets. It travels along null hypersurfaces, these surfaces in space-time that are moving at the speed of light. And the entropy, the information content, of that light is bounded by the area of the surface it's passing through. Light is nature's way of saturating the Bekenstein bound. Light is the thing that carries information in the way the universe fundamentally wants information to be carried. Your hard drive encodes information in the bulk of matter, in volume. Light encodes information on surfaces, and the limit on how much information can pass through a surface is set by area in Planck units. And a Planck area is about 10 to the minus 70 square meters. That is unimaginably small. The number of Planck areas on even a square centimeter is so enormous that comparing it to the number of bits on a hard drive is almost embarrassing. Let me give you some numbers, because I know people like numbers. A terabyte hard drive holds roughly 8 times 10 to the 12th bits. That's 8 trillion bits. Now, the surface area of that hard drive, let's say it's a flat disk about 10 centimeters across, is maybe 60 or 70 square centimeters. The number of Planck areas in those 70 square centimeters is approximately 10 to the 67. That means the theoretical maximum information that could pass through that surface in the form of light is something like 10 to the 67 bits, compared to the 10 to the 13th bits sitting inside the drive. The ratio is 10 to the 54. That's a 1 followed by 54 zeros. That is how much more information light can theoretically carry compared to the hard drive it could be shining on. Now, obviously, we're not anywhere near saturating that bound in any practical communication system. Your Wi-Fi isn't running at the Bekenstein limit. But that's not the point. The point is where the ceiling is. The point is what physics allows. And physics allows light to carry incomprehensibly more information than any material storage medium, because the fundamental limit on information is set by gravity and quantum mechanics together, and it's set by surface area in Planck units. And light is the thing that lives on those surfaces. But I want to go deeper than that, because we haven't talked about the most important thing yet. We haven't talked about what happens when you take quantum mechanics seriously. Classical light, light that you describe with Maxwell's equations, the 19th century description of electromagnetic waves, already has enormous information capacity because of all those modes I mentioned. But quantum light is something else entirely. When you quantize the electromagnetic field, each mode of the field can be in a superposition of states with different numbers of photons. 0 photons, 1 photon, 2 photons, a superposition of all of them. These are called Fock states, and they're indexed by quantum numbers, and the number of distinct quantum states available to even a single mode of the field is infinite. You have a countably infinite number of states, which means theoretically infinite information in a single mode. Now, in practice, energy is finite, so you can't actually use infinite states. But the point is that quantum mechanics gives electromagnetic radiation a richness of structure that classical physics doesn't even begin to capture. The quantum information capacity of light is vastly larger than the classical information capacity, which was already vastly larger than what any hard drive can store. This is why, when people started seriously thinking about quantum communication and quantum cryptography, they turned to photons. Not just because photons travel fast. They travel at the speed of light, obviously, but because photons can be in entangled states, superposition states, states that have no classical analog whatsoever. A pair of entangled photons carries correlations that cannot be replicated by any classical bit pair. Ever. That's not a technological limitation. That's a fundamental property of reality. Now, I want to take you somewhere that might seem like a detour, but isn't. I want to tell you a story about black holes, because black holes turn out to be the key to understanding why all of this matters at the deepest level. For a long time, and I mean decades, there was a serious scientific disagreement between myself and Stephen Hawking. I'm not being modest when I say he was one of the greatest physicists of the last century, but he was wrong about something. Specifically, he was wrong about what happens to information when it falls into a black hole. Hawking showed, in a calculation he did in 1974, that black holes emit thermal radiation. They glow. The radiation comes from quantum effects near the event horizon, and it has a temperature. This is called Hawking radiation. Now, the problem was that Hawking said this radiation was completely random. It carried no information about what fell into the black hole. Throw in a book, throw in a photograph, throw in a human being, throw in whatever you want. The radiation that comes out is just thermal noise. Pure randomness. And I looked at that and I said, that can't be right. That violates one of the most fundamental principles of physics, which is that information is conserved. You cannot destroy information. You can scramble it beyond all practical hope of recovery, but it's still there, in principle. Quantum mechanics requires it. This disagreement went on for about 25 years, by the way. I wrote a book called The Black Hole War about it, and eventually the physics community came around to my side. Hawking conceded. And the reason the physics community came around is something that's directly related to what we've been talking about today. The information that falls into a black hole is stored on the horizon. The event horizon of a black hole is, in essence, a surface. And according to the holographic principle, which I spent years developing, together with Gerard T. Hooft, the information content of anything inside the black hole is fully encoded on that surface. The horizon is like the hard drive. The universe inside the black hole is the file. And the Hawking radiation that comes out, the light that comes out, because Hawking radiation is thermal electromagnetic radiation, carries that information back out, in a scrambled form, in a form that is practically unrecoverable. But in principle, the information is there in the light. So here's the full picture. When something falls into a black hole, the information it contains gets encoded on the horizon, a surface, and then gets radiated back out as light. Light carries information was the whole message of the scrambling. The universe doesn't destroy information. It converts it into light and sends it back out. That's the holographic principle at its most stark. Information is not a property of matter. It's not a property of volume. It's a property of surfaces. And light is the carrier of information that lives on surfaces. Light is fundamentally more compatible with the deep structure of space-time than any piece of magnetic material stuck to a shelf in your bedroom. Now, I realize I've taken you from hard drives to quantum mechanics to black holes in a pretty short time, and you might be wondering whether this is all abstract nonsense or whether it has any practical consequences. And I want to be honest with you. Most of it is deeply fundamental and doesn't immediately change how you store your photographs. But some of it does matter, and will matter increasingly. The field of quantum communication is already using photons to transmit information in ways that are fundamentally secure, not just practically secure. Quantum key distribution, the technique of using entangled photons to create cryptographic keys, exploits exactly this quantum richness of light that I described. The security doesn't come from clever algorithms. It comes from the laws of physics. Any attempt to intercept the photons disturbs their quantum state, and you can detect the disturbance. You can literally tell if someone is listening. That's not a computer science trick. That's quantum mechanics. That's the information theory of light made real in a laboratory. And then there's the broader question of optical communication. The internet runs mostly on light now, fiber optic cables carrying information encoded in laser pulses. And the reason fiber optics beat copper wire isn't just that glass is cheaper or that light doesn't have resistance. It's that light, electromagnetic radiation, can be modulated at frequencies hundreds of trillions of times per second. That gives you an enormous bandwidth compared to electrical signals in metal. You can encode information not just in whether the light is on or off, but in its phase, its polarization, its frequency, all of that simultaneously. The information density is staggering compared to what electrons shuffling through a wire can achieve. So the practical takeaway is this. Light is not just a carrier of information. Light is the carrier of information in a fundamental sense. It's the thing the universe uses when it wants to move information from one place to another. It's the thing that saturates the bounds that thermodynamics and gravity set on how much information can pass through a surface. It's the medium in which the universe stores the contents of black holes. It is, if you want to take the holographic principle seriously, and I do, one of the deepest expressions of the fact that the universe is, at its core, an information processing system. Let me leave you with one thought, and it's something that took me a long time to appreciate fully. We live in 3 dimensions. We move through 3 dimensions. We build things in 3 dimensions. We store information in 3 dimensions, in the bulk of hard drives, in the bulk of CDs, in the bulk of whatever storage medium you happen to like. And our intuition about information is deeply 3 dimensional. More space means more room. More volume means more capacity. But the universe seems to have a different opinion. The universe seems to be telling us, through black hole thermodynamics, through the holographic principle, through the Bekenstein bound, that the real arena for information is surfaces, not volumes. 2 dimensions, not 3. And the carrier of information that is most naturally suited to surfaces is light. Light, which travels along surfaces in space-time. Light, which crosses horizons and carries their secrets. Light, which moves through the universe at the maximum speed allowed by causality. Your hard drive stores information in matter, fighting against the grain of the universe's actual geometry. Light stores information the way the universe wants it stored. That's not just an engineering difference. That's not just a question of terabytes versus zettabytes. That's a statement about the deepest structure of reality. And if that doesn't make you look at the light coming through your window with slightly different eyes, then I haven't done my job. Thank you.